Today we're going to take a look at an intro to exponentials. And specifically, we're going to take a look at where exponential equations are used. So you can title your notebook, Intro to Exponentials, because our new chapter is all going to be about exponentials and logarithms. So the first thing we're going to do is we're going to take a look at just a reminder of how you plug into exponential formulas. Just a quick reminder to make sure we're okay with all the functions of Desmos and how to raise things to a power and that sort of thing. So the first type that we're going to take a look at here, let me move this around so we can see it. We are given a culture of bacteria has an initial population of 72,000 bacteria and doubles every 10 hours using the formula. And we're given this formula where P sub t is the population after t hours, P sub 0 is the initial population, t is the time in hours, and d is the doubling time. So what is the population of the bacteria after 17 hours to the nearest whole number? So we have P sub t, P sub 0 times 2t divided by d. So P sub 0, our initial amount, well, we have 72,000 bacteria times 2, and then it says that t is our time here. So let me see if I can get this out of the way. There we go. So time, we want to know what is the population after 17 hours. So to the 17 divided by d is the doubling time, and it doubles every 10 hours. So we have to plug this into Desmos. So when you go to Desmos here, just a couple reminders here. So we have 72,000 times 2. Your power key is that a squared. I gotta make this a little bigger. I can't tell if it's going into the power or not. So to the power of, and then we had 17, that did not go into the power. Uh-oh. I'm having trouble here. You got to put everything in parentheses now to keep it in an exponent. So 17 divided by 10. So we have 233,929. So if we go back here, 233,929. We can plug that in here, 233,929. And sometimes it counts your answer as wrong, even though you might be off by a little bit. So always look at your answer because it depends upon where sometimes it rounds. So if you are close, you are good to go on these problems. So the second type that we're going to take a look at is exponential functions, but the basic. So our basic exponential function is y equals ab to the x, where a is our initial amount, x stands for our time, and b stands for our rate. And if something is a growth rate, when b equals growth, it's 1 plus our rate, where b, if it's decaying or going down, it's 1 minus our rate for that b value. So we always have to remember to do the plus or minus. So if we look at this question here, a new car is purchased for $17,600. So that's our initial amount, so $17,600. The car depreciates at 11.75%, so it depreciates, so 1 minus 0.1175 to the power of 11. So we can go back, and again, we'll use Desmos for this. So we have 17,600 times parenthesis 1 minus 0.1175 to the power of, whoops, I just did squared. So a to the b to the power of, and then we have 11 years. So it tells us 4450. So cars depreciate pretty quickly there. So let's put that answer in here and we'll see if we have it rounded correctly. And again, as long as your answers are fairly close, I'm okay. If it's off by a couple dollars, like this one, we had it off. So let's see. So, oh, I didn't round to the nearest cent. So again, if you see that on your answers, you know what you're doing. It was just a rounding thing. You can try another one if you want, or if it's just rounding, you can keep on going. So the third thing we're going to look at is exponential solving. And we're going to look at that basic one again. So again, we're looking at a times b to the x power. So if we take a look at these problems here, an element with a mass of 100 grams decays by 20.5% to a minute. To the nearest minute, how long until there will be 10 grams of elements remaining? So we have 10 equals 100. We know our rate, it's decaying, so 1 minus 0.205 to the x power, but we don't know the minutes. So when you're solving this one, I'm going to show you how you can use Desmos, because we haven't talked yet about how to solve an exponential equation, which we will be looking at how to find the exact answer this chapter. So we knew we started with 100 grams. So our equation was 100 times parenthesis 1 minus 0.2025. I think it was 20.5. So let's delete this. 0.205. But then we didn't know our power. So one thing we can do is we can guess and check. What happens after 10 minutes? Well, that's pretty close. Well, let's see. 11 minutes. 9 minutes. So I got a really good lucky guess. How to the nearest minute? Well, it looks like I guessed right away, and it was 10. But if you guess something way off, what if I said 200? We can see that that's way, way off. So we might, what about 50? Well, that's too small. 30, 20, 15, and we can see, take a look, these numbers are getting bigger. 11 and 10. The other way you could do it is we could put an X here, and we could write what's on the other side of the equal sign. And you'll notice, and if we graphed y equals 10, we can check where our intersection is, and our intersection is at 10.37. So if we went back here to our nearest minute, and we typed in 10, we can see that we got that one. But again, and you'll notice here, it's solving with something called logs. We're going to get to that in the future. For right now, I'm totally fine if you're just